The second potential energy we're going to deal with is the elastic potential energy. It's related to the work done by the spring force, the second of our conservative forces. So let's say I have a mass that's attached to the end of the spring, and I want to think about in which direction does the elastic force always pull on that mass. Well, what I know is the elastic force is always trying to pull the mass back towards equilibrium. So if I pull the mass out to the right by using some applied force, the spring force is going to point back to the left, back towards equilibrium. On the other hand, if my applied force pushes the mass to the left, then the spring force is going to point back to the right, again pointing back towards equilibrium. So I know that the elastic force, doesn't matter which way you move the spring, the elastic force is a restoring force, and so it's always going to point back towards equilibrium, which tells me that the spring is going to do positive work when the mass moves back towards equilibrium. So in that case, you're moving with the elastic force, and the elastic force does positive work. If you move away from equilibrium, well, now you're moving against the elastic force, and so that spring will do negative work under those circumstances. Given my definition that the change in the elastic potential energy is equal to negative the work done by the spring, well, if I know what kind of work the spring does based on how I move my mass, then I can figure out how my elastic potential energy is changing. So if the spring does negative work when my mass moves away from equilibrium, that negative work term multiplied by that negative sign out in front tells me that I will increase the elastic potential energy. So as I move away from equilibrium, I'm moving against the spring force and increasing the elastic potential energy. On the other hand, if I move back towards equilibrium, well, now the spring does positive work, and so that positive work multiplied by that minus sign tells me that I'm decreasing the elastic potential energy. The elastic potential energy increasing as you move away from equilibrium and move against the spring force. The elastic potential energy is decreasing as you move back towards equilibrium and move with the spring force. Well, we calculated out the work done by a spring as equal to negative 1/2 k times x final squared minus x initial squared, where k was our spring constant, and then x final and x initial were simply the initial and final displacements from equilibrium. If the change in the elastic potential energy is simply negative the work done by the spring, then those two negative signs are going to cancel, and I get that the change in the elastic potential energy is 1/2 k x final squared minus x initial squared, where again k is the spring constant and xi and xf are the initial and final displacements from equilibrium. So we want to check and again make sure that this equation is consistent in terms of telling us about when the elastic potential energy will increase or decrease. And so if I think about moving away from equilibrium, so that's the situation that's sort of pictured here, where I started at some initial displacement and moved farther away from equilibrium. That means that my final displacement is larger than my initial displacement. So my final displacement squared is larger than my initial displacement squared. So when I subtract final displacement squared minus initial displacement squared, I get something positive. K is always positive, times a positive number. Sure enough, I get an increase in the elastic potential energy. On the other hand, if I move towards equilibrium, then which one is larger of these two flips around. And so now it's my initial term that's larger. So the initial squared is larger than the final displacement squared. And so when I subtract in this order, I get something negative inside the parentheses. That negative times a positive k times a positive number tells me that the elastic potential energy decreases. So my equation is consistent with what I know has to be true about how the potential energy is changing based on whether I'm moving with or against the spring force. We could have gotten this equation for the change in the elastic potential energy by again starting from our definition and simply saying, oh, well, this is negative the work done by the spring, and so the work done by the spring, when I take care of the dot product correctly, means I've got a negative kx that I'm plugging in. These two negatives cancel. The k is constant, it comes out of the integral. I'm left with the integral of x dx, which ends up being 1/2 x squared that I need to evaluate at both endpoints. And so sure enough, that gets me the same equation. Again, if we want to talk about the elastic potential energy, what we mean is the elastic potential energy relative to the point where the elastic potential energy always equals zero. In this case, with our spring, we don't have a choice. The elastic potential energy is zero at equilibrium. But that means it's pretty easy to now calculate the elastic potential energy at any point. It's just going to be 1/2 times k times x squared, where again x is just, well, how far has your spring been stretched or compressed? The elastic potential energy can be zero. So if you haven't stretched or compressed your spring, meaning your mass is at equilibrium, then x is zero, square it, you still get zero, multiply it by 1/2 k, you still get zero. But what you can't get is something negative. So it doesn't matter whether you're stretching or compressing the spring. It doesn't matter whether you've moved to the right or to the left. That distance, it's defined as a positive distance, it gets squared, it gets multiplied by two positive numbers. So you always have something that's non-negative. You can have zero for the elastic potential energy relative to the 0 point, or you can have something positive relative to the 0 point. Delta US can be negative. So again, make sure it's clear whether you're interested in the elastic potential energy relative to the 0 point or the change in the elastic potential energy as your object moves from one initial point to a second final point.